Today we will dissect the Schwarzschild solution to obtain the coordinate geodesics and derive Kepler's third law for a circular orbit. The Schwarzschild solution is the simplest non-trivial solution to Einstein's field equation. It describes the spacetime curvature in the vacuum around a static spherical mass, such as a planet, star, or black hole, and it was discovered in 1916 by Karl Schwarschild. Setting z equal to 1, the Schwarzschild solution is this, and the Schwarzschild metric is this, where ds describes how distances between points are calculated on a curved manifold. The Christoffel symbols that describe the curvature are calculated using this equation, and the non-zero Christoffel symbols are these. The geodesic equations are the equations of motion for a force-free particle moving on a curved surface, and are calculated using this equation, where tau is the proper time experienced by the particle. Curvature causes the particle to experience pseudo-forces. Here are the four equations of motion. When dr by d tau is less than 0 for an infalling particle, the time coordinate experiences a repulsive force which is proportional to its own rate of change. Gravitational time dilation becomes exponential as a particle approaches 2gm, which is the event horizon of the massive object. However, if we apply the chain rule to get the below equation and set dr by dt equals to 0 for a tangential trajectory, we see that gravitational time dilation is constant. For distances larger than the event horizon, the acceleration due to gravity reduces to the Newtonian form, but near the event horizon, tidal forces transition to an r-cubed relationship, causing spaghettification to occur earlier. As the magnitude of dr by d tau increases, this repulsive term slows the infalling object's descent until it stops at the event horizon. The repulsive angular terms act as centrifugal force that causes orbital motion, but getting too close to the event horizon negates this effect, and the particle is still flushed away. Due to the spherical symmetry, we can ignore the geodesics in phi to get this simplified equation. The 1/r relationship with the angular velocity acts as a slingshot, as expected, from the centrifugal force, and results in gravitational lensing for light rays. The terms of all four geodesics work together to produce the famous characteristics of a black hole. To get Kepler's third law, we start with the radial geodesic, and we set up a circular orbit with the following parameters. We use the chain rule to split derivatives with respect to tau into derivatives with respect to coordinate time to produce this equation, which we're allowed to do due to the proof in part 1. Next, we use the fact that radial acceleration, radial velocity, and polar angle velocity are all equal to 0, and then we divide through by r minus 2gm and dt by d tau all squared to give us the following two equations. We see that d phi by dt is the angular velocity omega, which is equal to 2 pi over t, and t is the orbital period. If we substitute and rearrange for t squared, we get the final expression, t squared is equal to 4 pi squared over gm times r cubed, which is Kepler's third law.